Hello, Integrated Math 1. Welcome to lesson 2.1.1b. We're on day 2. So to kick things off with this whole let's relate our arithmetic sequences to our linear functions and make those connections. We did our first warm-up last time. We're doing our second warm-up this time. So on page M2-7, I have a new warm-up for you. It looks a little different than what we did before. Given the function f of x equals negative 3x plus 10, I'd like you to calculate f of 1, f of 2, f of 3, f of 4, and f of 5. All this means is that instead of an x, you're going to plug in a 1, solve it. Then instead of an x, you're going to plug in a 2 and solve it. Plug in 3, solve it. Plug in 4, plug in 5. That's all it means. All this notation means is you're just substituting for x. Whatever number's inside there, that's what you're substituting for x. So go ahead, hit pause, work all this out, and then hit play when you're ready to check your work. So to get this started, I'm going to plug in a 1. So instead of negative 3x plus 10, I'm going to say this is negative 3 times 1 plus 10. Negative 3 times 1 is negative 3 plus 10 is 7. Then I'm going to plug in 2. So instead of negative 3x, it's going to be negative 3 times 2 plus 10. Negative 3 times 2 is 6 plus 10 is 4. Pardon me, negative 6. Aha. Let's plug in a 3. Negative 3 times 3 is a negative 9 plus 10 is 1. Plug in 4. Negative 3 times 4 is negative 12 plus 10 is negative 2. And last but not least, if I plug in a 5, negative 3 times 5 is negative 15 plus 10 is negative 5. And there you go. There's your warm-up. So don't freak out over this. This just means plug in a 1, plug in a 2, plug in a 3, plug in a 4, plug in a 5. And in fact, I could put them all in order, just like an arithmetic sequence, right? I could say that's for 7, 4, 1, negative 2, negative 5. You might see some similarities to our warm-up from last time. Definitely some similarities there. So today we're continuing on with this whole let's make connections between our arithmetic sequences and our linear functions. Last time we finished off by literally turning our sequences into function form, right? We took our explicit formula, we turned it into function form. So we've already been doing some of our learning goals using algebraic properties to prove the explicit formula for an arithmetic sequence is equivalent to the equation of a linear function. We've already been doing that. We've already started, we're going to dig a little deeper on relating the defining characteristics of an arithmetic sequence, that first term, that common difference, right? That's what makes an arithmetic sequence an arithmetic sequence. And we're going to continue relating those to the defining characteristics of our linear functions. We know linear functions, the important things are the y-intercept and the slope. So we're going to also take it a step further, and eventually we're going to get to connecting the slope of a line to the average rate of change of our function. But we may not really get to that till next time, but that's okay. We'll have it in our HUD as we go. So we've already talked about conjecture. That's already come up, but our other key terms, I believe we're going to be looking at for first differences today. That's one that's going to show up today. And next time we'll be looking at for average rate of change. So we know that all sequences are functions. We know that our arithmetic functions give us linear sequences. So let's go to activity 1.2. We're all the way over on page M2-12. Notice we're in module 2 now. So page M2-12. At the end of the last show, stagehands at the community theater stacked the audience chairs and placed them in storage. The height of one chair is 34 inches. And as each additional chair is stacked, the height increases by 8 inches. So with this in mind, let's start thinking arithmetically. Can you use your arithmetic thinking with those first term and your common difference? And can you write an explicit formula to represent this scenario? Go ahead and hit pause, write it out, hit play when you're ready to check your work. So if you recall, the explicit formula for an arithmetic sequence was a sub n equals our first term plus our common difference times n minus 1. Well, in this case, that first chair, if there's just one chair there, it's going to be 34 inches tall. So I know my first term is 34, and then we keep adding 8 inches for each chair we put on. So it sounds like my common difference is 8. So here is my explicit formula. A sub n equals 34 plus 8 times n minus 1. Now, let's do what we did last time. Can we do what we did last time? I would like you to take your explicit formula that you just wrote, and you did write a lovely explicit formula. Can you rewrite it in function form? And I'll help you with defining the variables, but go ahead and start off by rewriting this in function form. Hit pause to write it out, hit play when you're ready to check your work. If you recall from last time, our first step was to turn our A into an F. So I did. So instead of A sub n, and actually I also changed my n's to x's. You could have left them as n's, that would have been okay, but I went ahead and changed them to x's. So instead of A sub n, I now have f of x. And that means instead of n minus 1, I just changed that to x minus 1. If you left it as an n, that's okay. But I know eventually I'm going to be doing graphy stuff, and so I kind of want an x in there instead. And you know what the next step is. We distribute this thing, right? We distribute 8 times x, 8 times a negative 1. Well, 8 times x is 8x. 8 times negative 1 is negative 8. We have like terms, right? 34 and negative 8. So I'm going to put my 8x in front, and then 34 minus 8 is 26. So I now have f of x equals 8x plus 26. Again, you might have n's instead of x's. That's okay. That's okay. That's okay. But I do want to define my variables. So real quick, x is the number of chairs, right? And f of x is the height of the stack. So I'm going to write that down. X represents the number of chairs, and f of x represents the height in inches of the stack of chairs. Awesome. Can you compare the two algebraic representations of this scenario, right? Because we now have two representations of this. Let me bring up my pen here. We now have our explicit formula, right? But now we also have this formula, our function form. So f of x equals 8n plus 26. Can you, we're going to compare these a little bit. So to start off for A, let's look at our explicit formula. How does the value of D relate to the value of A in our function form, right? Because we have this guy, we have f of x, if you recall, equals ax plus b. How is our D and our A related to each other? So a sub n, a sub 1 plus D times n minus 1. How is the value of D in the explicit formula related to the value of A in our function form? And how are they represented in the scenario? Make sure you include your units. Hit pause, jot down your thoughts, hit play to keep going. Well, I don't know about you, but I noticed that my common difference was 8, and I noticed that A, my slope, was also 8. They're the same. Yeah. The value of D and A are representing the unit rate, 8 inches per chair, right? And they're both 8. Keeping these in mind, be warned, I'm going to go to the next page and these are going to disappear. Can you now compare your A sub 1 in your explicit formula and your A sub B in function form? Can you compare the two? How are they related? Are they related? And how are they represented in the scenario? What kind of units are we talking about here? Go ahead and hit pause to write this down, hit play when you're ready to check your work. So in this case, and again, I'm going to bring up my formulas here. So we have our A sub n, and that was 34. There's our A sub 1. So my A sub 1 is 34, but in my function form, I have 26. Sorry, that should be an X. I have 26, not 34. So let's talk about that for a minute. The expression A sub 1 represents the first term of the sequence. Or you could even think of it as f of 1, right? What do you get when x equals 1? You get 34. That's what you get. And it represents the height of a stack with one chair. One chair in the stack, boom, that's what you get. So why is that a 26? The expression b represents our y-intercept, or f of 0, right? F of 0 of the function, that's what it represents. If I were to graph this on a graph, this would be where it hits my y-intercept, or where x equals 0. So b is actually f of 0, not f of 1. So that's why it's different. And it's kind of weird in this scenario because 26 inches isn't even the whole chair, right? 26 inches represents the height of one partial chair if you don't count the top 8 inches. So that's kind of weird in this scenario. So if a sub 1 represents the first term of the sequence, what does a sub 0 represent? And how can you rewrite the arithmetic sequence using a sub 0? You may need to think about that for a bit. Hit pause, give it some thought, hit play, and we'll discuss. So the variable a sub 0 represents the height of one partial chair. It just represents that height of that first chair, not counting the top 8 inches. So that would actually change our formula if it was a sub 0, because we would have a sub n equals a sub 0 plus d times n. And yeah, I know that seems weird. It is weird, so don't stress about it. In this stacked chair scenario, both d and a represented that additional 8 inches of height per one chair, or the unit rate of change. The common difference, d, of the explicit formula is the same as the slope, a, of a general linear function. And they both represent constant change. In a sequence, the common or constant difference is the difference in term values between consecutive terms, right? To get from here to here, it's 8. In a linear function, it's the slope, and it describes the direction and steepness of the line. It's the difference in your output divided by the difference in your input. Do you remember this formula? Do you remember this formula? Right? Do you remember this? If you have 2 points, you can find the slope. You subtract the y coordinates for your rise, and you subtract your x coordinates for your run. It's been a while since you've done this. It's been a while since you've seen this. It is going to be coming back. Yeah. So don't forget that that's slope. But we now know that's also your common difference. Yeah. So rise over run. Subtract your y values for your rise. Subtract your x values for your run. So when you see a graph or rewrite an explicit formula for an arithmetic sequence, right? We took our arithmetic explicit formula and we rewrote it in function form. It's apparent that it represents a linear function, right? It's pretty obvious. However, the structure of a table requires other strategies to determine whether it represents a linear function. So for a formula, it was easy, right? We just rewrote it and put it in function form. We're like, that's a linear function. Tables, though, work a little differently. So if you want to know if a table is a linear function, we've got to look at it from a slightly different perspective. One strategy is to examine what we call first differences. First differences are the values determined by subtracting consecutive output values. So where the input has an interval of 1, so your x's, your input is just like 1, 2, 3, 4. It just has a difference of 1, 2, 2, 2, 2, 2. Then the first differences are what you get when you subtract your outputs, when you subtract your y's. I'll show you what I mean in a second. If the first differences of a table are constant, the relationship is linear. So I'm going to show you what I mean here. The tables that represent the explicit formula and the function form are both here. So here's my explicit formula, my input, my output. Here is my function form, my input, my output. Now, we already know this is a linear function, but I'm going to show you how you can use first differences in a table. So we're over on page M2-13, and you have these lovely tables. So what we're going to do is we're going to determine first differences, okay? So what this means is I'm first going to check my x's and make sure we're just counting by ones. 1, 2, 3, 4, great. Because we're counting by ones, I can do first differences. And all you're going to do is you're going to find the difference between each of these. And do the same thing on the other table. 0, 1, 2, 3. Yep, that's all in order from 0 to 3. So I would like you may need a calculator to subtract and find your first differences. So because these are counting by ones, you can just subtract and find your first differences. Can you pause for just a moment, find the differences, and then hit play when you're ready to check your work? So I'm using my calculator. Of course I'm using my calculator. I love my calculator. To get from 34 to 42, I had to add 8. So I added 8. 42 to 50, I added 8. 50 to 58, I added 8. Same thing here, 26 to 34, I had to add 8. 34 to 42, I added 8. 42 to 50, I added 8. Now check it out. We got 8 every single time. Because my first differences are constant, I got the same first difference every single time. That means it is a linear function. So it seems fancy, it's not. So if you have a table, like I said, with an equation, it was easy. We just did our distributive property, combined our like terms. Hey, it's in function form, it's linear. For these guys, what we have to do is we have to check those first differences. If I have the same first difference every time, it's a linear function. If I had gotten like 8 and then 9 and then 10, I would have been like, oh, that's not linear. My first differences are not the same. So in both tables, the first differences were 8. So it was definitely a linear function. So Parks and Eva Kate agree that the table shown represents a linear relationship. Yep, they have this here. Woo, woo, woo. Because there's a constant difference between consecutive points. So they're like, okay, 1, 2, 3, 4, great, that's counting by ones. So they just subtracted, and they're like, hey, 5, 5, 5. Parks claims that the slope is 5, and Eva Kate claims that the slope is -5. Who's correct? They agree that there's 5s there, but Parks says that the slope must be 5, and Eva Kate says the slope must be -5. Who's correct and why? Hit pause, jot down your thoughts, hit play when you're ready to keep going. I'm noticing that as x is going up, my y is going down. Oh my gosh. So I'm actually subtracting 5 to get to the next one, aren't I? Oh my gosh, so that means Eva Kate is correct. Our slope is -5 because as my x values are increasing, my y values are decreasing. Yeah, it looks like the pattern is -5, -5, -5. So my slope is a -5, not positive. 5 describes how steep it is, and of course the negative describes the fact that it's going down, that it's decreasing in direction. So with this in mind, I've got a couple of tables for you. Number 6 on page M2-14, there's a couple of tables here. I can only fit one table at a time, but I have a couple of tables here. I would like you to find the first differences and then decide whether or not it is a linear function. So go ahead and hit pause, find your first differences, decide if it's a linear function, and then hit play when you're ready to check them. So to start this off, I'm checking my x's real quick because we want these to be in order. If I'm going to use first differences, we got to be in order. So 5, 6, 7, 8, great, they're in order. So I'm going to check these. So 12 to 15, I had to add 3. Oopsie, just kidding. 15 to 21, oh, I have to add 6. And 21 to 30, I have to add 9? Oh my gosh, that is not a constant difference. It keeps changing. So no, this is not a linear function. The first differences are 3, 6, and 9. It keeps changing. What about B? How'd you do on B? Again, I'm just going to check my y's. -2, -1, 0, 1. Great, we're going up, 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 up. 1. Fabulous. Now let me check my first differences. It looks like I subtracted 4 to get from 18 to 14. I'm going to subtract 4 again to get from 14 to 10. And I'll subtract 4 again to get from 10 to 6. Beautiful. They're all the same. So yeah, this is a linear function. Yes, it is a linear function. The first differences are all -4. Awesome. And for C, well, again, I'm going to do my double check on my x's. 10, 11, 12, 13. Great, just going up by 1. And now let's check our first differences. 1 to 4 means I had to add 3. 4 to 9 means I had to add 5. And 9 to 16 means I added 7. My first differences keep changing. They're not constant. I don't have a constant first difference. So no, it's not a linear function. My constant. It's not a constant. It's not a constant difference. It keeps changing on me. So my first differences didn't quite give me what I wanted. That's all right. As always, guys, I hope you found this helpful and I hope you found this useful. If you got questions or concerns, email me or come see me during office hours, during lunch. I'm around. Let's talk. And I'll see you guys later. Bye.